Right now, there's a good chance you're watching this on a perfectly flat piece of glass. You tap to pause, swipe to scroll, and you probably do it hundreds of times a day without a second thought. But if you think about it, a solid sheet of glass shouldn't know exactly what your hand is doing. It's a flawless electrical insulator, and there isn't a single moving part anywhere on the surface. We interact with these screens using muscle memory built from decades of pushing physical keys. We assume our finger is applying downward pressure to force an internal mechanism together. The secret to how your screen responds to you has nothing to do with downward force or mechanical switches. The missing hardware isn't inside the device. The secret ingredient making that screen react is actually the electrical biology of your own body. To understand how that biology interacts with the glass, we have to look backward. The core science making your phone work was invented before the first lunar landing. In 1965, a British engineer named E.A. Johnson was trying to solve a bottleneck for air traffic controllers. They needed a more immediate way to interact with the blips on their radar screens. Johnson coated a glass monitor with a thin layer of copper wire, creating the world's first capacitive touchscreen. It was massive and could only handle one touch at a time. For decades after, commercial devices mostly relied on a different method called resistive touch, like you'd find on a classic Nintendo DS or a supermarket checkout. Those screens use two flexible layers of plastic that require literal physical pressure to register a tap. But modern smartphones abandoned the pressure requirement entirely. When the industry shifted towards smooth glass surfaces, it reverted back to the logic of Johnson's 1960s invention. Your device completely ignores how hard you push against the glass. It is only sensitive to the specific material you are made of. If you look directly beneath the glass of your phone, you won't find a simple, solid layer. You will find a structure built from a fascinating material called indium tin oxide. It is a rare metal alloy that possesses two highly specific properties. It is an excellent conductor of electricity, and it is completely transparent. Manufacturers use this invisible metal to lay down a microscopic, tightly woven grid directly below the screen. While the phone is on, the battery pumps voltage through these transparent wires, generating a steady, continuous electrostatic field across the entire display. The screen is a highly energized net, constantly waiting for a biological trigger to disrupt it. That trigger comes from your biology. Human beings are basically walking sacks of salt water, which makes our bodies incredibly effective natural electrical conductors. Electricity naturally flows right through us. So, if we freeze time just as your bare finger comes within a millimeter of the energized screen, the moment you make contact, your body actually steals a microscopic amount of the screen's electricity. It absorbs a tiny fraction of the current from the grid. Because that current was siphoned off, the system registers an immediate drop in voltage. Sensors positioned around the perimeter of the screen calculate the exact X and Y coordinates where that energy went missing. The phone's internal processor takes that specific location data and translates it into a software command, opening an app or typing a letter, in a fraction of a millisecond. Every time you tap the glass, you perform an act of highly localized, intentional electrical theft. Bring that back up to real-time speed, and it happens so fast you never notice it as you scroll through your feed. It takes 1960s radar logic, perfectly transparent metal, and the biology of your cells, all working together in perfect synchronization. Put on a standard winter glove, effectively blocking that saltwater connection, and the glass stays dead. Without your specific chemistry, the device is completely useless. Every interaction with your phone relies on your biology to act as a biological component, completing a tiny and visible electrical circuit over and over again.